to welcome Dr. Mohammed Zidan, who is actually a professor in Hurghada Faculty of Computers and Artificial Intelligence in Egypt, and he will talk about non-classical computing problems toward a novel type of quantum computing problems. Mr. Mohammed Zidan, back to you. Thank you.
Thank you for you. It's my pleasure to be with you today, and I would like to congratulate you for this successful event.
We can't hear you well, Mr. Mohammed Zidan. If you can just maybe get closer to the mic. Yeah.
Are you hearing me now?
Yep. Yeah.
Okay. It's my pleasure to be with you today, and I would like to congratulate you for this successful event. Thank you. I hope you can see my presentation right now.
Yes.
Good. Today, inshallah, I will talk about another type of quantum computing problems. The main objective of this talk is that by proposing a simple modification in Deutsch's problem, we will prove that quantum computers solve some problems that are impossible to be solved by classical computers, even if these problems are quite simple. So here we will go make a simple modification in the definition of each problem, and then we will can prove that quantum computer will apply some problem and solve some problems that cannot be absolutely solved by classical computers. David Deutsch, who is the father of quantum computing, in 1985, he proposed the first problem that can be solved using quantum computers faster than classical computers. We know for n Boolean variables, there are 2 power 2 power n Boolean functions. So if n equal 1, then we have 2 power 2, which are 4 possible Boolean functions can be generated from a single Boolean variable x. We know that the Boolean variable may have 0 or 1. Then we can generate 2 power 1, which are 4. So the first function is f node, which is have constant value 0 for x equals 0 and for x equal 1. And the second function can be generated is f1, which once again has constant value 1 for x equals 0 and x equals 1. The third function can be generated is f2, which has f of x equals 0, f x equals 0, and has f of x equal 1, f x equal 1. The final function can be generated from this single variable is f3, which has f of x equal 1, f x equal 0, and has f of x equal 0, f x equal 1. These two functions are called constant functions, and these two functions are called balanced functions because number of zeros equal number of 1. Now, Deutsch's problem was given a black box UF such that this black box or oracle represents a Boolean function of a single variable, and this oracle can be represented or encoded using one of these 4 functions, and this oracle is unknown for us. The main goal of Deutsch's problem is that given this oracle, we need to classify it into one of 2 classes, constant function or balanced function. And we know that for constant function of 0 equal f of 1, and for balanced function f of 0 not equal f of 1. David Deutsch proposed the algorithm which can solve this problem on quantum computer faster than classical computers by 4 steps. In the first step, a quantum system of 2 qubits are initialized such that the first qubit is initialized in state 0 and the second qubit is initialized at state 1. Then, by applying the Hadamard gate on each qubit, then the first qubit will be transformed to kit 0 plus kit 1 over root 2, and the second qubit will be evolved to kit 0 minus kit 1 over root 2 according to the performance of Hadamard gate. Then, by tensor product, we will have the state of this system in this state. In the third step, the oracle is applied between the first qubit and the second qubit according to this rule. If the oracle applied between the first step, which is x, and the second step and the second qubit, which is y, the oracle will leave the first qubit keep as it is, and it will evolve the second qubit according to this rule. It will XORing y with the function of x. So by applying this rule on these 2 qubits, then the first qubit will be keep as it is. So here 0, and here 0, and here 1, and here 1. And according to this rule, we will make XORing between the second qubit with the function of the first qubit. So F0 XORing F of 0. And here is 1 XORing F of 0. And here is 0 XORing F of 1. And here is 1 XORing F of 1. Finally, the Hadamard gate is applied on the first qubit. So after applying the Hadamard on the first qubit, we will have state 0. We will have the first qubit in state 0 if the applied oracle or the applied black box represents a constant function. And we will have the first qubit in kit 1 or state 1 if the applied oracle or the applied black box represents a balanced function. So by measuring the first qubit, we will get 0 if the applied oracle represents a constant function, and we will have the first qubit in state 1 if the applied oracle represents a balanced function. Now let us review about the complexity of Deutsch algorithm. We know that this problem in order to solve this problem using classical computers, we need to call the black box or the oracle, or apply the function twice. One for x equals 0 and the another try for x equal 1. So we need to recall the oracle or the black box twice in order to solve this problem using classical computers. So the complexity of this problem on classical computers is of order 2. However, the previous Deutsch algorithm can be represented by this one circuit, and it is crystal clear here that the black box is called only once. So the complexity of Deutsch Deutsch's algorithm is of order 1, and by this explanation, it is clear that quantum computers can be solve some problems faster than classical computers. In this talk, we will make a simple modification. Given an unknown qubit, kit t equal alpha kit 0 plus beta kit 1 in a pure state, such that modulus alpha greater than 0 and modulus beta greater than 0, and modulus alpha not equal modulus beta, where modulus alpha squared plus modulus beta squared equal 1. The second given is that an oracle represents a Boolean function of a single variable which is applied on kit T. And we need to achieve two goals. In the first goal, we need to classify the oracle UF into one of two classes. Is it is constant function or balanced function? Then we need to estimate modulus alpha and modulus beta with some relative error epsilon. But we need to mention a remark here. If modulus alpha equals 0 or modulus beta equals 0, then the proposed problem is converted to the standard Deutsch problem. In order to propose algorithm to solve the proposed problem, we will use quantum computing model based on entanglement degree. This model was proposed such that given a quantum state psi of T that is represented as a state of a quantum system of n qubits, such that its state is initialized or given as a known state. Then we attach two ancilla qubits G and H, and we apply the oracle which represents a Boolean function of n qubits, such that the input of the Boolean function is represented by psi of T, and the output of this function is encoded in the qubit in the kit G. Then we apply an operator, we double it MZ operator. This operator creates entanglement between these two qubits G and H, and the degree of entanglement between these two qubits depending on the state of the qubit G. Then we measure the degree of entanglement between these two qubits. After we measure the degree of entanglement between two qubits, we can solve the problem at hand based on the degree of entanglement using one of two techniques. The complete mathematical framework of this model and how can we implement this model using the circuit model is described in details by this paper. And this computing model was used to solve some quantum computing problems and some quantum machine learning problems. And these are the papers which are published so far using this computing model. Now, what is entanglement in general? We know that for an arbitrary composite system of two qubits described by a state xi is called two qubit entanglement system if and only if it cannot always be written mathematically in the product form. So if we have a two qubit system and we cannot write it as a factorization of the first qubit into product, second qubit, or as a product form, then we call these two qubits are entangled. However, this definition cannot quantify the degree of entanglement between the first qubit and the second qubit. In 1989, authors proposed the concurrence as a measure of the degree of entanglement between two qubit system, and this paper was published in 1989. For simplicity, if we have a two qubit system defined by this state, kit xi equal d node kit 00 plus d1 kit 01 plus d2 kit 10 plus d3 kit 11, then the concurrence can quantify the degree of entanglement between these two qubits by this relation. The concurrence of xi equal 2 modulus d1 times d2 minus d naught times d3. And the concurrence always is bounded in the interval 0 and 1, such that if the concurrence equal 0, then there is no entanglement between the two qubits. And if the concurrence equal 1, like then the entanglement between these two qubits is maximum, like Bell states. And if the concurrence between 0 and 1, then the state is weakly entangled. However, there is some issue in this form. The main issue of this form that cannot be calculated on quantum computers, because we know that if we need to make any computing problem, we must use unitary transformations. However, this form cannot be implemented on quantum computers. Indeed, there are two quantum circuits can be used to implement this circuit. One of them is Romero and Dian circuits, which was published in this paper with Romero at Physics A. In this circuit, we will take two independent copies of the qubit. We need to quantify the degree of entanglement in between. Then we apply sigma y in the third qubit, and we apply sigma y in the fourth qubit. Then by applying CNOT gate between second qubit and fourth qubit, then we apply X followed by H on the second qubit. Before measuring this system, just after we apply these gates, the state of the four qubits are described by this state. Now we know that the concurrence between the two qubits T and D is quantified by this formula. If we compare this formula by this state, we will see that the probability amplitude of the state 0, 0, 0, 0 and the probability amplitude of the state 1, 0, 1, 0 can be used to quantify the concurrence between the two qubits T and D quantum mechanically by these two forms. So we can use these two forms to quantify the degree of entanglement between two qubits using circuit model. And the complete and for further details and the complete mathematical framework for this circuit is explained in this video. Now let us remember our problem again. We are given two guys. First, we have an unknown qubit T equal alpha kit 0 plus beta kit 1, and an oracle represents an unknown Boolean function in this form. And we need to classify the oracle into one of two classes and estimating the modulus alpha and modulus beta with some relative error epsilon. Our proposed algorithm is that first we initialize the quantum system using two qubits. The first qubit is the given unknown qubit alpha kit 0 plus beta kit 1. Then we attach an ancilla qubit kit D, which is initialized in the vacuum state 0. So the state of the system at the initialization step is alpha kit 0, 0 plus beta kit 1, 0. Then we apply the oracle according to the rules which we mentioned before, that we keep the first qubit as it is, and we evolve the second qubit by zoning the second qubit by the function of the first qubit. Then we repeat steps step 1 and step 2 to obtain another copy of the state of psi 1. And here we must note that here we didn't violate non-cloning theorem, because when we repeat step 1, we will initialize a new independent quantum system. So we will have two independent copy of the state of psi 1 without violating the non-cloning theorem. Then we apply the Romeo circuit, and then we estimate the concurrence value using this formula. Concurrence equal root 2 time bs, where bs is the probability of the state 0, 0, 0, 0, and the probability of the state 0, 1, 0, 0, and the probability of the state 1, 0, 1, 0, and the probability of the state 1, 1, 0. Here, our formula is quite different than Romeo, and we will explain this in the analysis of the proposed algorithm. So if we have concurrence equal 0, then the applied oracle or the applied black box represents a constant function. And if we have concurrence greater than 0, which means that there is entanglement between the two qubit T and D, then the applied oracle represents a balanced function. And if we need to estimate the value of modulus alpha, then we use the fourth root of 2 time probability of the state 0, 0, 1, 1, or probability of the state 0, 1, 1, 1, or average of them. And it's easy to calculate modulus beta by this form. Here is the circuit model of the proposed algorithm. Here T is unknown, we take two couple of them, and then we attach two ancillary qubit in state 0. Then we apply the oracle on each replica. Then we apply Romeo circuit. Let us analyze the performance of the proposed algorithm. In step 1, we just attach the ancillary qubit T to the unknown qubit. So the state of the system will be alpha kit 0, 0 plus beta kit 1, 0. In the second step, we apply the oracle UF according to this rule. It will keep the first qubit as it is, and it will evolve the second qubit according to this rule. It will evolve it by observing the second qubit by the function of the first qubit. Here we will study each case in detail. In the case f0 equal f1, which represents one of the two constant function f0 or f1. If we have uf represents f0, which f0 equal f1 equal 0, then after applying the oracle between the two qubits P and D, the state of these two qubits will be alpha kit 0, and then we know that f of 0 is 0, so 0 tensor product is 0, and here 0 tensor product is 0. So we will obtain a product state such that the first qubit T is alpha kit 0 plus beta kit 1, and the second state remain as it is. So there is no entanglement between the two qubits T and D. So after we applying this part, after we applying this part, which is coming from Romeo circuits, we will obtain this state alpha beta 0, 0, 1, alpha square 0, 0, 1, 1, and so on. So if we need to quantify the concurrence using this form, such that Bs equal probability of the state 0, 0, 0, 0, and B and the probability of the state 0, 1, 0, 0, and the probability of the state 1, 0, 1, 0, and the probability of the state 1, 1, 1, 0. It is clear that probabilities uh, are zero. So there is concurrence between there is value for the concurrence, and it is expected that there is no entanglement between these two qubits T and D. Now let us show if we have also if we need to quantify the modulus alpha squared. It's clear that by taking the average value of the probabilities of the state 0011 and the state 0111, so we can quantify the modulus alpha by this formula, and it's very easy to find the value of modulus beta. Now, if we have UF represents the function f1 for which f of 0 equal f of 1 equal 1, then after we applying the this rule, so 0 XORing f of 0 XORing f of 0 here is 1, so 0 XORing 1 is 1. And here we will apply this form. So 0 XORing f of 1, and here f of 1 equal 1. So 0 XOR 1 is 1. Once again, the state of these two qubits T and D are represented as a product form or factorized form. So there is no entanglement between the two qubits T and D. So we will expect that when we measure the concurrence, it will be 0. After we apply the Romero circuit, so which we did before, we will have this state. Now, if we need to quantify the concurrence quantum mechanically using quantum computers, we need to quantify the probability of the state 0000 and so on. And if we see here, all of these probabilities are zeros. So the concurrence equal 0 as we expected from this state. And once again, if we need to estimate the modulus alpha, we will take the average value of the probabilities of the state 0011 and the state 0111, and it's very easy to estimate modulus beta. On the other hand, if the applied oracle represents constant balance function, in balance function we have two functions which are f2 and f3. So suppose that the applied oracle or the applied black box represents the function f2, and we mentioned before that f2 is f of 0 equals 0 and f of 1 equal 1. So by applying this rule, the state of the system after applying this rule is here 0 XORing f of 0. So 0 XORing f of 0 and the function and the value of the function of 0 is 0. So 0 XORing the 0 is 0. And here 0 XORing f of 1 and f of 1 is 1. So 0 XORing XOR 1 is 1. Here it is crystal clear that this state cannot be factorized and cannot be written as a product form. So these two qubits are entangled, and the degree of entanglement between these two qubits can be calculated by 2 modulus alpha beta. So such that C here is greater than 0, and its value depends on the state on the value of alpha and beta. So after we applying Romero gates, we will have these states, and we will expect that if after we quantify the concurrence by this form, it is obvious here that the probability of the state 0000, which is alpha beta not equal 0, and the probability of the state 0100 not equal 0, and the probability of the state 1010 not equal 0, and the probability of the state 1110 not equal 0. And here it is clear why we quantify the concurrence slightly different than Romero gates. So when we measure the concurrence here, it will be greater than 0, which represents that the applied oracle or the applied black box represents balanced function. And it is obvious here that modulus alpha can be quantified by the mean or the average of the probabilities of the state 0011 and the probability of the state 0111. And it's very easy to calculate modulus beta. And the final function, the applied oracle may be F3, and we know that if in F3 f of 0 equal 1 and f of 1 equal 0. So when we apply this rule in this state, we will have that 0 of 0, and we have f of 0 equal 1, so 0 XOR 1 is 1. And here 0 XOR f of 1, and here f of 1 equal 0, so 0 XOR 0 is 0. Once again, we cannot factorize this state, so there is entanglement between the two qubits T and D, and the degree of entanglement between these two qubits is 2 modulus alpha beta. So we will expect that when we quantify the concurrence by quantum computers, it will be greater than 0. So the state of the 4 qubits after we applying the gates of Romero circuits will be in this state. So we will see that the probability of the state 0000 is greater than 0 for state 0000 and for state 0100 and for states 1010 and for state 1110. So the concurrence here is greater than 0. So we can conclude that if the concurrence is 0, then the applied oracle represents a constant function, and if the concurrence is greater than 0, then the applied oracle it represents a constant, a balanced function. And in all cases, we show that modulus alpha can be calculated or estimated by estimating the probability of the state 0011 and the probability of the state 0111. Now, what about the error of estimating the concurrence value on quantum computers? Without more details, here is the error of estimating the concurrence value using quantum computers, such that BS represented by the probabilities of these states. And the error of estimating modulus alpha can be estimated by this form, and all these calculations are explained in details in the published paper. Finally, we realized the proposed algorithm using IBM quantum computer. So for implementing the 4 functions, F0 is implemented by the circuit shown in figure number 8, and the second function is implemented by the circuit shown in figure number B, and the third function is implemented by the circuit explained in figure number C, and the final function is implemented by the circuit shown in figure number D. Then we repeat 3 experiments. In the first experiment, we assume that the unknown qubit is given in this state with 1/4 for kit 0 plus 3/4 for kit 1, and we applied the 4 functions. Then we repeat the experiment and we assume that the used qubit is root 1/3 kit 0 plus 2/3 kit 1, and we apply the 4 functions. Finally, we repeated the four functions for kit 0 in the uniform distribution. And we by implementing this quantum circuit on Qiskit and IBM quantum. And here is the results. It is clear that such that the blue bars represents experimental results, and red bars represents the theoretical results, and green bars represent the simulation using Qiskit. It is clear that for the experimental and the simulation matches the theoretical results very well. And here is the estimated modulus alpha using the proposed algorithm. And here is the statistical fidelities of implementing our algorithm using IBM's 5-qubit quantum computer. And finally, we proved our analysis using quantum state tomography using IBM quantum computer. The main results of this talk were published in this paper. As a summary, in 1985, Deutsch proposed the first algorithm that shows that quantum computers are faster than classical computers. In this session, we seen that by proposing a simple modification on Deutsch's problem, we prove that quantum computers solve some problems that are impossible to be solved absolutely by classical computers, even if these problems are quite simple. Here, this algorithm or this paper will open our eyes into another type of quantum computing problems that cannot be absolutely solved on classical computers, and this will help us to make a significant progress in drug discovery, such that if we can implement IBM, if we can implement quantum computers to modify the fluctuations or random mutations in DNA using this type of problems, then we will make significant progress in drug discovery. Here is my email for any further questions. Thank you.
Okay, thank you, Mr. Zidan, for presentation. Let's see if we have some question from the audience. Okay, so we have one question actually from Dr. Osama. Thank you, Dr. Zidan. It was not clear to me how much is the speed up of the proposed quantum algorithm compared to the same classical one. Would you please talk more about the advantage of this quantum algorithm?
Please repeat the question again. Please repeat the question again, please.
Yeah, oh well. So the question from Dr. Osama, it was not clear to me how much is the speed up of the proposed quantum algorithm compared to the same classical one. Would you please talk more about the advantage of this quantum algorithm?
Okay, thank you, Professor Osama. Here, there is no comparison between the complexity of the algorithm on quantum computer and on classical computers, because we have a known qubit, and we know that unknown qubits cannot be implemented absolutely using classical computers, because we don't know what is the value of absolute alpha and what is the value of absolute beta, because the qubit is unknown. So here there is no comparing the complexity. So this is another type of problems that can be solved using quantum computers only, but cannot be applicable on classical computers. I hope my answer is clear to you.
Okay, thank you, Mr. Zidan, for your answer. Another question from Dr. Murad. Can your proposal, thank you, Dr. Zidan, can your proposal be generalized to Deutsch-Jose algorithm?
Of course, it's very easy to generalize it using our model. I will back. It's a very good paper. One can apply it to, and one can read it by. I will try to apologize. Yeah, Prof. Anwar, using this model and this paper, you can generalize it for Deutsch Jose problem. It's if someone read this paper, it's very easy to generalize it for Deutsch Jose when you have an oracle and you apply on unknown quantum state of n qubit. Moreover, this model can be used to solve a huge number of problems and quantum computing problems and can generalize for any unknown quantum system because we know that teleportation open our eyes that we always we have unknown qubits can be received. So it's okay. You can use this model and this paper to solve a generalized version of the problem.
Okay, perfect. Thank you, Mr. Zidan. I mean, with that, we will close our event. I would like to thank you all for your listening, for your interactions. I would like also to thank all of our speakers for their valuable presentations and for their answers and stuff. So